Good afternoon, everyone. Indeed, today I would like to present this new Python package for deduplication. I called it Deduplipy. And before I start, I indeed want to give a bit of introduction about myself. So born and raised in the Netherlands, I studied physics. And then I started working for ING Bank 11 years ago. I had various modeling positions. And in the last years, I mainly focus on detecting money laundering and other types of financial economic crime in transactions. And this is how I started to work on the interesting topic of deduplication. Before we jump to the package, I would like to first explain you a bit about what deduplication means. The task of deduplication is basically to identify the single real-world entity from different notations. And another word for deduplication is entity resolution. On the screen, you see 11 company names in different representations, but they are not 11 different companies. Actually, when you apply deduplication, you see that there are basically 3 different companies. So this is what humans are very good at and what's also useful to let computers do. There are basically 2 challenges when it comes to deduplication. The first challenge is, how do we compare 2 strings? The most well-known string similarity metric is the Levenshtein edit distance. This is basically the number of changes you need to make to one string to transform it into the other string. And then that is a measure of string similarity. However, a different entity can have a smaller Levenshtein distance than for a different notation of the same entity. Let me show you this with an example. So here you see the pair Airbus and Airbnb. You want to compare them. And as you can see, you need to change 2 characters to transform Airbus into Airbnb. So their edit distance is 2. And it's a different company, obviously. If you look at the second case, there is the Airbus Group SE and Airbus. This has a larger edit distance, so the string similarity metric is larger, or the distance metric is larger. So basically, if you look at the characters only, the second pair is more dissimilar than the first pair. However, the second pair is the same company, the airplane manufacturer, and the first pair are really different companies. So basically, you cannot choose a string similarity metric, set a threshold, and say, above or below the thresholds, the representations belong to the same entity and vice versa. So the first challenge is, how do we compare 2 strings? The second challenge in deduplication is, what comparisons are you going to make? If you would naively compare every string with every other string in the data set, you get an n-squared problem. The number of comparisons blow up, and it's not computationally feasible to do all the calculations. So if you have n strings, then the number of comparisons becomes n times n minus 1 over 2. Let's take an example. Spotify has 70 million tracks, and there are duplicates in it. These are not really the same tracks, but these are variations in orchestra, for example, for classical music, or they are remixes, etc. If you would deduplicate this data set with all the possible comparisons you can make, you would end up with a number of comparisons that is just unfeasible to calculate. So the second challenge in deduplication is to select which comparison you need to make in a smart way. Entity resolution or deduplication has drawn a lot of attention from academia. If you type entity resolution in Google Scholar, you find like 11,000 articles. And even over the last years, you still see new articles popping up, lately mainly with the application of deep learning. Still, I thought that I could add something to this space. So I created the package Deduplipy. The idea of Deduplipy is that it's a deduplication package that works out of the box. So you can just create an instance, fit it, and predict it just as any other scikit-learn model. However, the reason why I created this is that I wanted to be able to tweak and tune some advanced settings for the more experienced users. I work in a bank, we have very big data, and sometimes we just need to be able to tune things because of the large data that we deal with. And I couldn't find that yet in the packages that were available. Let me show you how Deduplipy solves the two challenges in deduplication that I mentioned earlier. First of all, this n-squared problem. Most, if not all, deduplication approaches first apply blocking to the data. And then you only compare the pairs that fall into the same block. Let me show you how this works. So the first step is that you apply a large list of blocking rules to the data. And these blocking rules can be things like the same first word or the same first three characters, the same integers, etc. There is a whole bunch of blocking rules implemented in Deduplipy, and in principle, you don't need to worry about that. It happens all under the hood. Then Deduplipy uses a so-called greedy set cover algorithm to take the smallest set of blocking rules that maximizes the inclusion of the positive training labels. So it's basically the most efficient set of blocking rules that you should use for comparing all the individual representations. And we only compare the pairs within the same blocks, and thereby we reduce the number of comparisons by a lot. So if you look on the right side of this slide, you see a data set that I created myself based on Stoxx 50 companies, Euro Stoxx 50 companies. And if you would naively compare everything with everything, then the amber shaded region would all have to be compared. If you apply a blocking rule, let's say the first word, so you only compare pairs where both representations share the same first words, then only a fraction of it, the much smaller region you see on the screen, has to be compared. And Deduplipy allows you to easily add your own blocking rules or to choose your own blocking rules. And that is something that I really needed for the problems I work with. Remember that the second challenge in deduplication was how to compare two strings. And Deduplipy solves this problem with a very simple logistic regression model that is trained on features that are the similarity metrics. So in Deduplipy, we use the Fuzzy Wuzzy package. It's a package on PyPy that implements a lot of string similarity metrics. So for all the pairs that we found during the blocking stage of the process, we calculate a bunch of string similarity metrics. So you see here ING Bank, and V, that's a pair. And then you calculate a bunch of string similarity metrics. And you do that for all the pairs in your data. Well, as I mentioned, I think it's important that the more experienced users can choose their own settings, so you can also apply your own similarity metrics. And that is very simple. The only thing you need to do is create a function that takes two strings and outputs a number. So here you see an example. Let's say that you want to include as a feature whether or not the first word of two representations match perfectly. Then you can implement it yourself like this and add it to the Deduplipy instance. So at this stage, we have per pair, we have a number of string similarity metrics, and these are then used as features for a logistic regression model that is trained on these, that is trained to predict whether a pair is a match or not. And for this, I use scikit-learn under the hood because that is like a perfect implementation. As a user, you can also choose to include interaction features. And with that, you can, scikit-learn basically includes the products of all the individual string similarity metrics. We then apply L1 regularization to make sure that you don't overfit, and basically thereby apply a feature selection. So this way, we score all the pairs within the blocks and go to the next step. So how do we train this classification model? You could take a bunch of data samples or a data sample and then label all the combinations in there or so. But that's a lot of work, and most often the majority of the pairs are not a match. So that's the reason why we use active learning here, as implemented by the modal package. In active learning, you create an interactive session where the user enters for each pair that is presented, whether it is a match or not. And this is a very efficient way to collect training data and quickly have a trained model. So how it works, you present all the pairs that you found in your blocking stage. And then the model is applied to the data, and then the data sample, so the pair in this case that the model is most uncertain about, is presented to the user. The user then gives a yes or a no whether it's a match or not. That data point is added to the training data, the model is retrained, and the process continues. And you continue doing that until you have a converged model. And this generally with Deduplipy, you have a converged model in like well 20, 30 of these steps. It goes really fast. The question then is, how does Deduplipy, or model I should say, how does it measure the uncertainty? And that's actually pretty simple. It is just 1 minus the probability of the most probable class. So let me show that in this little plot. There are 3 data points. The amber dots indicate the data points and the prediction of the model. And as you can see, the most left and the most right data points, there is a small uncertainty. So there is the score is close to 1. But the point in the middle has a much larger uncertainty. So when you do active learning, this will be the data point that will be presented to the user, and the user should then give input whether it's a 0 or a 1, whether it's a match or not. Let's have a look how this active learning works on a data set. And for this, we use the North Carolina voter registry data set. It's a data set that is more often used for deduplication, and is provided by Professor Erhard Rahn. The data set consists of 3 columns: the name, the suburb, and the postcode. And there are a lot of duplicates in it. As you can see, the first 2 are most likely duplicates. There are 2 representations of the same person. So Keymerk Thomas is written in 2 different ways here. Then he lives in Charlotte suburb. And there is also a typo, and there's a G instead of a 9, or an OCR error. I don't know what the source is of this data. And the task is here to identify which rows belong to each other, which rows belong to the same real world entity and person in this case. So let's have a look how this uncertainty evolves over the training of the Deduplipy instance. Here we look at an uncertainty heat map. On the horizontal axis, you see the similarity of the names, and on the vertical axis, you see the similarity of the suburbs. Because I wanted to create a 2-dimensional plot, I could only use 2 columns and just 1 similarity metric per column. Then on the bottom left, you see the dissimilar names and the dissimilar suburbs. So these are the cases where most likely it's not a match. And on the top right, you see the more similar names and the more similar suburbs. So there's a larger probability that the pair is a match. Then the colors indicate the uncertainty. So on the bottom left, you see a lot of green. There's very low uncertainty, and that is logical because if there is no similarity in the name and no similarity in the suburb, it's most likely not a match. On the top right, you see that there are much less dots, but there's a lot of white, and that is just because there are not so many matches in the data. But there you also see some greenish colors here, and that's also logical because if there is very large similarity in both the names and the suburbs, it's most likely a match. And in the region in between, you see a lot of red. So there is the high uncertainty. So these are the pairs that will be presented to the user. This is the uncertainty heat map after 2 labeled pairs. Then the Deduplipy will present the most uncertain pair to the user, and the user needs to enter whether it's a match or not. And the pair that is presented is shown here in the plot. So in this case, I would say this is a match, although there are some typos in it. After 4 pairs, the plot looks like this. And if you continue labeling, you see over time that the area of the red area, so the uncertain area, gets much smaller. And after 15 labeled pairs, the model is converged. So now you see that really on the bottom left, of course, it's a lot of green. So there is no uncertainty. These are just no matches. And on the top right, you see there's also a good green area indicating that the model is not unsure. So it's sure about the positive, the matches of the pairs. Okay, so we first started with the blocking stage. Then within the blocks, we calculated the similarities of the pairs. using this interactive learning. And the next thing that we do is that we are going to create a network of pairs and probabilities. For this, we use network X. And in this graph that we create, every node is a representation. It's basically a row in our data set. And every edge between the nodes is the pair that is scored. And the edge weight, the numbers you see in the lines, is the probability that was output by the logistic regression model. The first thing after creating this network that we do is we apply the connected components algorithm. And the connected components algorithm distinguishes the subgraphs in the graph, where every subgraph is not connected to any other node in the same graph. So in this case, you see that it's clear that there are 3 subgraphs that can be created by the connected components algorithm. We now go a step further, and we are now going to apply hierarchical clustering to obtain the clusters. And the clusters are then the final deduplication results. So here we see 2 of the 3 graphs from the previous slide. On the left side, you see all the Banco cases. So these are 2 companies, Banco Bilbao and Banco Santander. And as you can see, here you see the dendrogram of the hierarchical clustering. That algorithm is able to distinguish, based on the probabilities in the graph, which representations belong to the same company and which belong to a different company. And the value of hierarchical clustering becomes more apparent if you look to the graph on the right. There are 3 different companies, Deutsche Börse, Deutsche Post, and Deutsche Telekom. And as you can see, there are large probabilities, like this 0.78, 0.87, between instances from Deutsche Post and from Deutsche Börse. So that means that the classifier basically would say this is a match. But because we have a graph, because we have a network with all the probabilities in it, the hierarchical clustering takes into account also these cases, these edges with very low probabilities, and thereby creates clusters of the things that are that belong to the same entity. So this really shows the value of hierarchical clustering, because the classifier on its own would say that this is a match. So I would say let's have a look at the demo. Let's have a look at the code and see how Deduplipy works. Deduplipy is obviously hosted on GitHub, so you can clone it there and you can look at the example notebooks. Deduplipy is shipped with 2 data sets. We now look at the voters data that you saw earlier. Here are again the name, the suburb, and the postcode columns. And we are now going to create a deduplication instance, and we are going to provide some advanced settings. The simple case with the out-of-the-box mode, so to say, you can try yourself, but I can show you how to do some more advanced settings. Let's say that we want to choose the similarity metrics ourselves per column that we want to apply. Let's say so from Fuzzy Wuzzy, we import some of the string similarity metrics that you can find there. And we create a dict that we call field info. And for every column, so name, suburb, and postcode, the 3 columns in our data set, we enter a list of the functions that we want to use to compare those strings. Let's also say that we want to define the blocking rules ourselves. And let's say we are not interested in blocking rules that apply to suburb and postcodes. We only want to apply blocking rules to the name column. And let's say we only want to see the first 2 characters. This can be useful in some cases. If you have very small data, you probably want to you don't bother about blocks being too large. On the other hand, if you have very large data, you do want to have your blocks a bit confined. So this is something you can play with if you run into troubles on your particular use case. So furthermore, we say interaction is true. So that basically means that you want to include interaction features between the columns of your data set. And what happens under the hood, what I showed you earlier, is that scikit-learn then includes the product of all the string similarity metrics. So for example, partial ratio on the name times token set ratio of the suburb. And as I said, when we use these interaction features, then the logistic regression classifier applies L1 regularization. Furthermore, we set verbosity to 1 to get some more information during the process. And we create the deduplicator instance with the things that we defined before. And then during fitting, the actual active learning starts. Now the sample is created under the hood, and we get presented the cases that we need to label. So here we see we need to answer yes or no, whether this pair is a match. So you have name 1, suburb 1, postcode 1, name 2, suburb 2, and postcode 2 for Rebecca Bauer Bond. The first 3 cases are always perfect matches, and we do that to help the active learner package to have a good start. Here we see Rebecca Bauer Bond and Dara Puri. That is obviously not a match. Not a match. And if you continue over time, you see already right now, after only 6 labels, that the case that is presented here is already, they are already much closer, right? This Shawnee and Shawnee is sort of similar. The suburb is the same, and the postcode is also the same. But yeah, it must be a typo, so I guess this is a match. Willie Green and William Reynolds. Let me continue a few cases more. And as you can see, after a while, you get information on the uncertainty. So the last uncertainty improvement that you see here, that is basically the biggest uncertainty improvement that you saw during the last, I think, 5 iterations. And the uncertainty is just uncertainty as I explained in the slides. Let me label a few more. No match. I think this will be a match, right? Robert Smith, Roberta Smith, Maxton, don't think so. Floyd Key, there we go. No match. Okay, so if you continue a bit more, then you will get the message that the model has converged because the uncertainty is not improving anymore, or because the uncertainty drops below 0.1. But let's say for the sake of time, we are finished. And what happens now is that you get a score histogram. And these are the scores that are calculated on the data in your sample that you didn't use for training. So obviously the majority of the scores are very low because the majority of the pairs are not a match. Then in the middle region of the scores, there's nothing. And that's also logical because otherwise they would be presented by the active learning package. And then you see a few cases that have a large score, and these are most likely the duplicates. So the active learning is finished, the blocking rules are found, and in this case, that's the first 2 characters of the name. But it is trivial because that's the one that we defined here, and we only presented 1 blocking rule to the user, to the package. So then we have our trained deduplicator instance, and then we can use it to predict it on our data that we have here or on new data. And what we can now do is we can say, well, the majority of these scores, these very low scores, they will not end up in the same cluster. It is not really likely that a 0.05 probability of a pair will belong to the same company. So what we can say, and that's useful, especially if you work with large data, is that you put a threshold on the similarity probability of, well, in this case, 0.1. And that can make the computations much faster because there are just fewer computations to make. So here we see the results. We have in our original data frame still the columns name, suburb, and postcode, but now we have an additional column that's called Deduplication ID, and that basically gives a number to all the rows that belong to the same entity, in this case, the same person. And as you can see, Lucille Richards has the same Deduplication ID. Luta Baldwin, same story. And then here we have even a case with 3 rows that belong to the same person. So the deduplication ID number itself is meaningless, but it's really about which rows have the same number. Well, we now applied it on the data that we trained it on, but you can also save your deduplicator instance using Pickle and load it again from this and apply it to data, and you will get exactly the same result. So this is in a nutshell how it works. You can have a further look in the notebooks that are on GitHub. And let me then go back to the presentation. So this was the presentation of the Deduplipy package for deduplication. I have more ideas to further develop the package. I would like to test neural networks instead of the classification, the logistic regression classifier. And you can basically follow the work already on in one of the branches. But I'm very open to ideas from the PyData community. So please feel free to contribute. You can find the address here on GitHub. And I'm happy to take any questions now.
Thank you so much, Frits. We have a couple of questions here. The first question I'll read, it's from Mark Andre. Mark Andre asks, is it possible to also get the uncertainty for each deduplication ID?
Yeah, no, that's not implemented. So what you can set, and I didn't discuss that here, you can set thresholds for the clustering, and thereby you can increase the recall or the precision, yeah, depending on if you increase the threshold or lower it. But the uncertainty, so basically the quality of the cluster, that is not given. No, but I'm looking forward to a pull request for that.
Okay, thank you so much. We also have another question from Aikona. Aikona asks, is it possible to customize presentation of user decisions to make it easier to compare?
You mean the representation in the notebook where you see the pairs? Again, I'm open for other ideas. What you could do, I saw there's a new package that's also dealing with similarities. SimCity it's called, and the one who developed that uses Pigeon for in Jupyter notebooks. If you use something like that, it's indeed more user friendly. It looks nicer, but on the other hand, it doesn't then work from the command line. But yeah, you could definitely propose something.
Okay, we have a couple of questions here, but we only have 2 minutes left. One question asks is that how do you train blocking rules at the same time with similarity scoring or in active learning?
Yeah, no, so I know that there are other solutions that do it at the same time. In Deduplipy, I do it as completely different independent steps. So it's really first, the blocking is done independently from the scoring.
Okay, thank you. And the other question asks is, how do you plan to consider domain knowledge in the matching
domain knowledge, yeah, I understand. In the matching algorithm, yeah, so the domain knowledge is basically implicit while you are training it. So if you, that's basically what I showed here. So the domain knowledge in this case, the example that I gave here, could be that I see that a 3 could be an E, right? Because there was some, I think, OCR errors in the names. So this is basically something you provide implicitly while training the Deduplipy instance.
Okay, I think we can squeeze in one last question. Lucas asks, is it possible to use already labeled data with duplicates or no duplicates for training?
Yeah, good question. The idea behind Deduplipy that it's a very simple package to easily and quickly get a deduplication instance that is trained on using active learning. There is no functionality yet to include already labeled data, but I can imagine that is valuable. On the other hand, I have to say that normally you get conversions in like 20 or 30 cases, so that goes really quickly. Again, if you have a pull request, I'm happy to take a look at it, but it shouldn't save you so much time if you use the excellent active learning as implemented by Modal.
Okay, thank you so much, Frits. I'm certain If there are any questions left unanswered, they will connect with you on GitHub and on all your socials. Thank you so much.
Thanks a lot.